second unit is really the basic tools we will use to describe continuum mechanics. So we're going to spend some time understanding these operations involving tensors. And what do you know about tensors? What have you heard, or have you heard anything? Have you encountered this term before?
Just in the reading.
Just in the reading, what did you understand, or what do you know about tensors?
So it's like a vector, but it also involves stress. What I understood.
Okay.
So.
We'll revisit that.
Okay.
Have you encountered this word before?
Yeah.
Okay.
But I can explain.
But you can't explain. Okay. Do you know about this term before?
Like if you just have this one directional stress, you can use vectors, right? But if the body has different body act differently from different directions, you need different coordinates and more coordinates. So we use tensors.
Okay. So some of that is sort of raw, but we'll try to polish it. Tensors are not just about stress. You should first understand that they are a mathematical entity which describe different quantities. Okay, but they are not just about stress. I want to make that clear first. So the classic thing is when you draw your forces. Let's say you have an infinitesimal cube. You are used to seeing this in a force balance sense. So if this area is A, and let's say this is x-axis, this is y, and then this is z, the stress acting on this surface, if the shear stress, let's say the shear stress on this surface. So if I draw the shear stress acting this way, okay, we would give it a nomenclature that it is tau x and z. That is, the stress is acting on this plane normal to the y direction. So we denote two directions. For example, this stress involves two directions. But the reason I'm saying this is to emphasize tensors are not only meant to describe stress, they can also describe other quantities. Like, for example, think of a non-spherical shape in a flow. I'll give you time to write. Okay, after every 5 minutes, 10 minutes, I'll take a pause, give you 2 minutes to write. So this is more about a discussion. So just don't worry about writing for now. So think of a non-spherical shape in a flow. Suppose you are bicycling. Okay, you are what you are. You are not an exact sphere. You are not a symmetric shape, and you are going in the wind. But sometimes what happens is the wind is blowing around your face or around your body, and sometimes exerts a lateral force on you. Even though the wind is blowing on my face, there could be a lateral force on you which is kind of pushing you sideways. So what I'm trying to say is we have a non-spherical shape. Here's a flow. We'll give the flow like vector u, which is mostly directed along this direction. But because the flow can turn around the object, can turn around and go over. What happens is that sometimes there is also not just a force along this direction, but also in the lateral direction. So you could have, we'll call this direction as x, we'll call this lateral direction as y, and we'll call the lateral, this upward direction as z. So you could have a force Fx, which is equal to the drag coefficient times u or ux. Okay. You can also have a force along the lateral direction, and I'll call this Cxx for a reason you'll see now. Cxy or Cyx ux. It's like saying I'm interested in the y component of the force due to a flow that is in the x direction. And that is possible because this object has some non-spherical shape. The flow mechanics and the micro details of the flow result in a lateral force. And don't think this is alien to you. You would have experienced this if on a really windy day, if you're bicycling. For no reason, you'll be falling sideways, even though the flow is on your face. So the thing that I'm trying to connect through here is, it is customary to write the drag force equal to a drag coefficient multiplied by a velocity, where this drag coefficient is a scalar. But I just established through qualitative arguments that this drag force can have components that are due to not just the velocity along a particular direction. It's like the flow is moving this way, but the force is not just along this way, it's along this way and also this way. And this is for the same reason a helicopter takes off. A helicopter encounters a flow in one plane, but because of the rotor motion, it also experiences lift force, right? So I can rewrite this and say the drag force is this time a drag coefficient tensor dot velocity, which I can expand as cxx ux plus cxy uy plus cxv uz. This is fx, fy, fz. So I can write a relation between different components of a vector and another vector. Remember, this is a vector, this is a vector, and here is a tensor that is connecting the two vectors. Now, I didn't care to define the term vector, which I just assumed you would know. At least two of these terms, I assume you know. Scalar and vector. And we'll talk about tensor. The basic fact I want to first convey is that tensors are not just about stresses. Tensors are quantities that connect different quantities which depend on a frame of reference or a coordinate system. So this vector depends on a frame of reference on a coordinate system. So does this vector also depends on a coordinate system. Whereas in between you have this tensor that doesn't depend on the coordinate system. It's like a universal property of the flow and the shape, which doesn't depend on either the flow velocity or the magnitude or the way you measure the drag force. Is that making sense? The fact that you are a 5'10" person who weighs 170 pounds and your dimensions are what they are, those dimensions determine this drag coefficient through fluid physics. It doesn't depend on the coordinate frame you use to describe this whole process. A tensor at a basic level is a mathematical entity which contains physics and is independent of the frame of reference in which you carry out an observation. So let me write that down and then I'll give you time to write. Tensors, this is my own definition. This exact word may not be in the book, but I feel this is more physical to convey. Tensors are mathematical entities which contain the physics of a process or interaction and is independent of the quantities and the frame of reference in which quantities and the frame of reference in which the observations are made. And when I say quantities, usually I'm talking about a cause and an effect. I'll tell you what the cause here is. The cause in this case is the velocity and the effect is the drag force. Something happens and something happens because of that. When you write stress, for example, when you write stress equal to a Young's modulus, I'm sorry, wrong example. So when you write a force due to a spring is equal to a spring constant times displacement. If you write it that way, in a conventional sense, your K is the spring constant, which is scalar. Now, if you have a funky spring, which has properties like if you apply a force in one direction, it also has a deformation in other two directions. That relation would be written as K dot X, where K will expand similar to this. Okay, so let me come back to the statement here. Tensors are mathematical entities which contain the physics, and they are expressed in a way that they are independent of the frame of reference or coordinate system used. That part is very important because every observer will have a own way of, or have their own frame of reference, which now brings me to that word. I need to define this. Okay, and the whole study of continuum mechanics uses tensors because think about this. A material or a sample has many atoms. We discussed that last time. Whatever macroscopic deformation that you measure should not depend on the microscopic details of how these atoms are arranged or what every atom does. It shouldn't depend. So that's why we want to use tensors which kind of encompass all those details in a way that it's universal and doesn't depend on whether you have a cylindrical coordinate system or a Cartesian coordinate system, or whether you are moving, you are not moving. Those kind of details should be irrelevant. The deformation should be the same regardless of who is describing. That is why we use tensors. Okay, I'll take a pause. If you want to write something down, please do. Then we'll continue. Yes.
You mind if I take pictures?
Yeah, sure. I'm also recording. What I plan to do is every 3 or 4 lectures, I'll post it, but you are welcome to. Okay. This also is not exactly a kind of common definition for tensor. Even the book in the very first paragraph, chapter 2, says tensors are tricky to define. It's like initially it's mysterious, you don't know what it is, but you keep repeating that word and keep using it again and again. You start doing problems. Over time, you still don't know what it is, but you kind of develop a familiarity. And after a while, it's so familiar that you stop asking what it is. I'll give you some examples of quantities which you have been dealing with your entire life, but never bothered to define. This one is easy. If I say what is entropy, we all kind of have that mystery about it. We don't know what is entropy. Each person will say one thing. But can you tell me what is energy? You can define potential energy, you can calculate kinetic energy, but what is energy? It's to make a point. It's one of those quantities that you're being told from, from your school days. You just accept it at some level and stop asking what is energy. Like you can calculate kinetic energy, but can you tell me what is energy? I can't. So this is the same thing applies to tensors for me. For me, I've been handling tensors. After a while, I stopped trying to define it. You can have a definition saying tensor is a quantity that obeys a certain mathematical relationship, but that is not a very satisfying definition. So I gave up and just accepted tensors. It's like having a wife. You stop questioning and start accepting. Once you accept, your life will be simpler. All right. So I want to start with this term that I used. Frame of reference. You want to start with this term. The word itself is a definition. It's like saying, for reference, I'm choosing a particular way to measure distances and a certain point in time, which I start my clock. From there on, I start measuring or counting time. Okay. So a frame of reference is essentially a coordinate system wherein we designate a point as the origin and three orthogonal or perpendicular, mutually perpendicular directions to define a vector or to define a direction. And this frame of reference can be at rest or moving with a constant velocity. It can be accelerating or accelerating or rotating or combinations thereof. Some of it you might already know. These things you might have seen already, but good to put them in one place. Okay. So a frame of reference is a coordinate system wherein we designate a point as origin from where we measure all our distances. Like for example, you could take this room, make that corner the origin so that you can measure all distances from that point or all vectors from that point. And we can make the three directions of the three lines at the corner as the x, y, and z. So you can try to use that, those three directions. Basically, you have three perpendicular directions, right? In mathematical language, these are called basis vectors for the vector space, which in this case is three-dimensional physical space for us. So if you have three basis vectors, you define a 3D space, two basis vectors, it's a two-dimensional space and so. So this frame of reference is nothing but a coordinate system which can be at rest or can be moving with constant velocity, or it can also be accelerating or rotating. Now, this was, at least until here, is the understanding that existed until Newton's time, where he thought that if we could be in a frame of reference which is absolutely at rest, or maybe it is even moving with constant velocity, but you can't tell the difference between two. That is, if you are in an elevator that is falling at a constant speed, from inside you can't tell whether you are falling or not unless you look outside. You will try this experience if you are in a skyscraper, if it has enough floors for you to experience that uniform velocity drop. You cannot say whether you are moving or not. But what do we know about the real world now after Newton? There's nothing in the solar system which is at rest. Really, or not even solar system, nothing in the universe that is truly at rest, or if it is at rest, you can't tell that it is rest because you are not at rest. Everything is moving as part of either a galactic or a star system or a planetary system. So this is really a idealization which doesn't exist. So we think that in this room, if you do an experiment of deformation or some kind of physics experiment, you can consider this room to be an inertial frame of reference until when? You look outside, the outside still looks nice and like the buildings out there are not moving. Until you encounter a situation where the experiment is comparable in length scale to the dimensions of the Earth, so that the Earth's curvature starts becoming important. And then you look at outer space, then you realize that Earth is moving until it starts interfering with that. So for most of our solid mechanics or theoretical perspective, we can think that our frame of reference is at rest and get away with it because think about it, we are taking a small sample and doing a compression test or some kind of experiment with that, which is confined to small length scales. It doesn't matter if the Earth is rotating or not rotating. But if your experiment is entering those higher length scales, then it becomes a problem. So for our course, at least this is the first time you are learning continuum mechanics. You might be doing more courses, but for us, we'll think a inertial frame of reference. That's what this is called. This is referred to as an inertial frame of reference. It doesn't exist in reality, but we will assume that it exists and we will do problems because it vastly simplifies the mathematics. If you are in an accelerating frame of reference, can you give me some examples? It should be easy to think of something that's accelerating. Car, where you are not car, it's just car. Car in which you are pressing the accelerator, where you are actively accelerating. What else? Rockets, any propulsion system in which you are actively moving forward, where your velocity is changing. Or if you are in any system that undergoes rotation, rotation itself is a form of acceleration. You can't rotate without accelerating. So these are all called non-inertial frames of reference, which are little mathematically more challenging. So in our first attempt in this topic, we won't go there. We'll just stay with inertial frames. Okay. So in all of our discussions, our coordinate system, which would be Cartesian, cylindrical, spherical, whatever, it doesn't matter. Let's say we have three basis vectors, E1, E2, E3. We'll assume that the vectors are basis vectors are constant in time, so that they are not changing. And we designate an arbitrary point as the origin of time. It's completely arbitrary when you start the observation. And from then on, we are interested in what happens after our observation starts. This is the premise in which the entire course will go on. Yeah. So by that logic, if you are in that inertial frame of reference, we already kind of understand that being at rest and being at constant velocity is one and the same thing. You just have to subtract the velocity and you're back to being at rest. So we won't separately discuss this possibility, but you have to solve a problem in which you are falling in an elevator at constant speed and you are doing an experiment. So it's like a frame of reference which is moving at constant speed, constant velocity. That case is nothing but same as the other case. Okay. So all this is stuff you know. Okay, so don't I'm not. So the book, the text also discusses the problem with this assumption. There is, of course, the assumption is not technically correct, but it is still pretty reasonable. You should be aware of situations where this won't be a good assumption in general. Those will be anything that is accelerating, anything that is moving closer to the speed of light, or anything that is rotating. Those situations are to be dealt with differently. Anything relativistic? No, we are not going there. Okay. Can I erase this side? So we'll start with this basis vectors. I'll call them E1, E2, E3. I can also write it equivalently as EI, and I can take values of 1, 2, and 3. The basis vectors, I already said, we'll deal with those that are mutually perpendicular or orthogonal. What that means is E1 dot E2, E2 dot E3, E3 dot E1 is 0, or you can write EI dot EJ equal to delta IJ, where this function takes a value of 1 if I equal to j and 0 if I is not equal to j. And this function is called the Kronecker delta. If you see this, is any part of your mind telling you I'm talking about Cartesian vectors? Yes, no, yes. How did you come to the conclusion?
Given that the directions.
So you're seeing this and thinking X, Y, and Z direction. You just automatically made that connection. But what I wish to tell you is you don't have to just always think these orthogonal vectors are always Cartesian. So when we think of other coordinate systems, like for example, this is the way I've drawn this, this looks like a Cartesian, okay, XYZ coordinate system. So suppose if I think of a cylindrical coordinate system where let's say this is E3, which we commonly refer to as the z-axis, or I'll write E3. Okay, and if I take any point, you can express it as x and y. You can also alternately express it as, so let's say this is a plane and this is say z equals z1, and in this plane this is r and this angle is theta. So you can write this is r cos theta, r sin theta in that plane. And if I add one more, that is the coordinate z, I can define this direction as E1 or E radial. If I have a circle, the radial, what is radial direction? Starting at the center, if I draw a line along the radius and infinitely extend it, that becomes the radial direction. And the direction that's perpendicular to the radial direction would be the tangential direction, which will say E2 or E theta. So for simplicity, if I draw this here, this is E1, that is ER, and this is E2, which is E theta. If I take any particular point, this is R cos theta, R sin theta. So the ER vector, so this is the origin. So the ER vector is here, E1, ER, and the direction perpendicular to that is E2, which is E theta. So if this ER direction is cos theta, cos theta I cap plus sin theta j cap, E theta direction would be 42. What would E theta be? If you rotate this by 90 degrees, what are you going to do?
Sin theta minus
Sin theta. So essentially I'm rotating it by 90 degrees, right? Theta plus pi by 2 plus sin theta plus pi by 2. So this will be sin theta. Cos theta plus pi by 2 is plus sin theta minus cos theta. Okay, so you have three mutually perpendicular directions, which could also be 1, 2, and 3. So the first thing I want to break through is, whenever we refer to as E1 into E3, don't picture it as Cartesian always. It could be cylindrical, it could be spherical, it could be any mutually orthogonal set of vectors that form a coordinate system. Okay, so we will occasionally encounter this also. In fact, if you think of a deformation on a shape, suppose you take a shape like this looks very much like a cylinder, right? And if I start twisting it, I'm applying a force and I'm going to get the atoms to move around and this shape is going to change. The study of continuum mechanics is to predict those shape changes in response to an applied force. So this shape looks like a cylinder. So maybe it's natural for us to describe it in terms of an axial vector and a radial vector and an azimuthal vector and so on. But what about a shape that looks like this mouse? This is neither a sphere nor a cylinder. So what is the best set of three directions to describe this object? In general, in general, you can't control or you can't just build theories for just specific shapes. The problems you're going to encounter in your work or your engineering applications can be anything. So how do you think of the best set of directions to describe a given shape? Is it always Cartesian? No, of course not. Then what's the best set? Cylindrical?
Yeah. Initial point, reference point.
Okay.
And
Let's get some other answers because you're saying cylindrical. Okay, let's see what other answers are. Yeah. Somebody said something.
Can take a point like what you said, both the directions are correct.
So you have no control over the shapes this object is going to go through. That is, I'm taking this marker. Every type of loading that I do is a deformation operation. I can apply tension, try to stretch it. I can bend it. I can twist it. I can compress it. You can do this in very many combinations. So at the end of all this might not even be remaining as a cylinder anymore. Do you see that? The shape is a very transient thing, and basing your coordinate system, the way you describe this whole mathematics on a shape that won't even exist for throughout the experiment is pointless. Would you agree with me? So then what is the best way to define or to define directions that can act as basis vectors for writing down the equations? That is the question. At this time, you don't have to answer the question, but would you just agree with me that blindly choosing Cartesian or cylindrical or spherical or whatever is not going to be useful? If you just agree on that, down the line, I'll tell you the answer to that question. Okay? So, we talked about basis vectors. They are mutually orthogonal. Any three mutually orthogonal vectors can form a coordinate system or be a basis vector. So let's write that down. Any three mutually orthogonal, in mathematical terms, we call it linearly independent vectors can act as a basis for a coordinate system. So then the question that we will defer to answer is, what is the ideal or natural set of basis vectors for any given shape? Euler eigenvectors. You have heard of it, eigenvectors, right? If you have a matrix, you can calculate the three eigenvalues and corresponding eigenvectors. Does it ring a bell somewhere? That is the answer. So that's a spoiler. So if you didn't want the answer, you should have shut your ears. So we'll come back to this. We'll use it throughout later part of this unit as well as in the next chapter on kinematics. Okay. So those who want to take picture, write this down. Okay. So the lot of definitions and conventions that we learned initially will make it seem like we are not moving anywhere, but suddenly we'll move and move quickly. Okay, so don't fall asleep, bring some coffee. All right. So first thing we are going to see is we still haven't defined what is a tensor. I just want to remind you that, but we'll still try to build the infrastructure around that. The first infrastructure is called indicial notation. Indicial notation. So what do I mean by that is, if I take a vector v, I can write this as v1 e1 plus v2 e2 plus v3 e3. It's like saying if e1, e2, e3 are my basis vectors or three principal directions, and the component of its velocity along each direction is v1, v2, v3, the vector is nothing but v1 times that unit vector plus v2, e2 plus v3 times the unit vector. The indicial notation is shorthand to write this as vi, ei, and you can write this with a summation I equal to 1 to 3, but this is where the convention comes. The first of those is called the summation convention, which is if an index appears twice, once on a quantity and other time on another quantity, then summation is implied or assumed. So essentially what I'm saying is this summation symbol I runs from 1 to 3 vi ei is simply written as, is simply dropped, and this is equal to this and a shorthand for representing this. So when we write v equals, when we write a vector v, we just write vi ei. That's it. That's the summation convention. And Einstein's name is associated with it. It's called Einstein's summation convention. So that you would think it's a very smart thing to do. So we want to start, we want to go back a little and ask what is a scalar and how is it differing from a vector? Basic question. You know this. What is a scalar? Only magnitude. It's a pure number, or it's a number which doesn't have any sense of direction associated with it. It's like saying mass is mass regardless of what direction you are thinking of. It doesn't depend on orientation in any way, right? Energy, speed, magnitude of a vector in general. Whereas what is a vector? Can you give like a physical example? Force, it's improper to say force without telling along which direction you are applying it, right? So when we talk about a scalar has no dependence on direction, vector is denoted with the direction always. I mean, I don't really go by textbook definitions. I just write what is on, what I really understand. Okay, I'm not, you can't find these exact definitions anywhere. These are things I make up. Okay, hopefully not incorrect. So when we write a scalar m, or when we write a vector, say velocity v, we know that m is just a single number. If you just have a single number, there is no need for you to have an index associated with it. Why? What do the indices denote? They denote directions. You sum over 1, 1, 2, and 3 over the 3 directions. So when you have a scalar, automatically you can think a scalar has no index for the same reason that it doesn't depend on direction. So there is no need to denote an index for a scalar. Whereas for a vector, it intimately depends on the 3 directions. We write it as vi, ei. So this scalar has no index. This vi, the components, they are also scalars, but have an index to denote to which direction that component pertains okay. So like saying this index or this number of indices involved here, which we'll call as order, is 0 for a scalar, whereas for a vector, order is 1. 1 is essentially the number of indices involved in completely, not incompletely, involved in completely specifying. You can see where I'm going with this. We'll add one more versus tensor. Okay, so now we have come to the point where we have to define this tensor. I can't postpone this anymore. I've been dragging this for 1 hour now. Okay, so let's start with a physical situation which you can relate. So if you take a cube, like a material that is in the shape of, let's say, a cube, you know this familiar diagram. So let's say we'll call this X, call this Y, or sticking with our convention E1, E2, and E3. So take a listen, don't worry, I'll give you time. So if I take this top face, we'll call this the 1-3 phase, because it's defined by E1 and E3 directions perpendicular to the direction 2. So we'll call this the 1-3 phase. On this 1-3 phase, there are three ways you can apply force. What are the three possibilities? You can have a force that is along direction 1. You can have a force that is along direction 2. You can have a force that is along direction 3. Only three possibilities, right? So how do you compute stress? What is our basic understanding of what is stress? Stress is force applied per unit. This is what we learned from high school, right? So what are the three possible ways you can calculate that stress here? Three. What are those three? That is, you can write F1 divided by, we'll call this A13, F2 divided by A13, and then, 1 second, F1, A13, A13, and F3 divided by A13. Right? One of these is a normal force, two are tangential forces. You know this. So we'll take this F1 divided by A13, which is a shear force. We'll call this tau 13. Okay. We'll call this tau 12 because this is a force along 1 on an area perpendicular to 2. So tau 12 will define as F1 divided by A13, knowing that A13 is always perpendicular to 2. And then the second quantity is tau 22, which is F2 divided by A13, which is perpendicular to 2. So since this is the normal force, we'll use a different symbol. We'll call it sigma 22. In accordance with convention that we always follow to show normal stresses with sigma and shear stresses with tau. Nothing physical about it. Okay. And then we'll also write tau 13, which is F3 divided by A13, that is perpendicular to 2. All three are stresses, but they are different quantities, right? So this stress here, the component of stress, which we still don't know what it is. We are still talking about a stress without even referencing whether it's a scalar or a vector or a tensor. We'll just keep the mystery. This component of stress depends on two directions. What are those two directions? It depends on the direction of the force and depends on the orientation of the area. Two independent directions are determining this component. You're with me? That number 2, that two independent directions are determining this component makes the order of this component 2, one for each direction. If three independent directions determine this component, order would be 3, 4, 5, and so on. There are tensors that are third order, fourth order that are, or even eighth order that are involved in certain materials. But for most of our purposes, we'll work with 2 or 3 only, or maybe 4, not more than 4. But if you are into novel exotic materials, they have properties that depend on 8 different orientations. So to change something at a point, you have to do something in some another directions, something like that. But is this kind of connecting with you? The stress at a point, the component of stress, if you want to specify it completely, you need to know what's going on in two directions. What is the direction in which the force itself is applied, and what is the orientation of the force or orientation of the area with respect to that force. Two, I keep saying that two is what is the order, because two numbers or two directions determine that component. Okay, so this is order two. I'm still very reluctant to say that this is a tensor. Like I'm almost so eager to write a tensor with two dashes. It has 9 combinations. I can write sigma 11. I can write tau 12, tau 13, and then tau 21, sigma 22, tau 23, 31, 32, 33. These 9 numbers you can think are the various possibilities for this cube. Do you agree with me? Right? This is the 9 possible ways you can obtain the stress for each phase, and 3 possible ways of getting that force or applying that force. These 9 numbers, this set of 9 numbers are the components of a tensor if and only if they obey a certain condition. Let me write that sentence down. These 9 numbers are the components of a tensor if they obey a certain condition or mathematical relationship. What could that relationship possibly be? Is it some magical equation that you have never heard of? There's nothing about acceleration or anything here. We don't even know whether this is a real real material with the mass or anything. It's all hypothetical at this stage. All we are talking about is a volume in space that looks like a cube, and can I apply forces on each face? So there is nothing really physical here. So what could this mathematical constraint be? You? Yeah.
Sigma 11, sigma 22, and sigma 33.
Okay, what about them? See, suppose this cube is really some material like water or iron or some object, something that has atoms. What is stress, first of all? I'll tell you one thing. Tensors are not just about stress, but stress is a very good way to illustrate tensors. That's why I'm talking about stress at this point. So what is stress first? When you're thinking of applying a force like a shear force or a normal force on a little piece of material, you say you are stressing that material or the material develops and stress. What is that? Yeah. What do you understand when you say that material is stressed? So I have this piece of iron, I am stretching it or I am compressing it. What's happening to that material?
Deformation.
Deformation is nothing but the atoms are getting displaced from where they were. Right? Deformation is nothing but a bunch of atoms moving from where they were in the previous instant. So you can take a material subject it to a series of deformations or series of applied forces on it. And each time its shape will change in response to the applied force and the material's nature. Could be an elastic material or a plastic material, gooey material, could be something like clay, which just takes the shape of how you do this. So stress is nothing but a manifestation of the internal forces between the atoms. When you try to take them away or when you try to squeeze them together, they develop internal forces which manifest as stress at a macroscopic level. Is this something we all can agree or have? So is this our common understanding? That stress is basically a response to atomic response to the applied force. Okay. That response of those atoms, it would be silly to think that that response or the stress that is developed is dependent on the coordinate system that you use to describe the problem. You, the observer, who is completely disconnected from that material, it's silly to think that the way you describe this process will affect the process. Is this making sense to you? Like, for example, if you are observing something, you could have a name for it, but that name has no bearing on what's going on. Right? It's similar to that. So it's like saying the stresses, the components of the stress are nothing but the stress values in each pair of directions. So like in vector, it's just easy. You just say a number per direction. It's like you have to say a number per pair of directions. For every pair, there is a number. This tau depends on two directions. The sigma depends on two directions and so on. So it's silly to think that your choice of coordinate systems should affect the stresses developed. Do we agree on that? So we need a way to calculate these stresses which are independent of the choice of coordinate system. You can do this problem with a set of basis vectors. You can do this with a different set of basis vectors. And if both of you are calculating the stress at a point, you both should get the same calculation or same answer. That is the mathematical relationship. Instead of saying certain conditions, that condition is nothing but the components should transform between coordinate systems such that a few parameters remain invariant. Again, I am adding a word few to keep the mystery going on. What is this few? Which parameters should remain invariant? How to calculate those parameters? For that we have to actually do the work. We can't just talk in abstract sense. Okay, but that 9 numbers, you can't just take arbitrarily some 9 numbers and call them a tensor. They have to obey certain rules of transformation so that your frame of reference between you and you, whoever is observing, all those observations should lead to one conclusion or one value for the measured stresses. Is that making sense? Yes, no? Okay. All right, so by starting to talk about order, we say that scalar is a zeroth order. The vector has order 1, and we can think of a second order tensor like stress, which depends on each number depends on 2 directions. It's like saying scalar, the number depends on no directions. Vector, the component depends on one direction, whereas a tensor like stress, tensor such as stress, not tensor doesn't equal to stress, it is an example. The stress tensor, each component depends on 2 directions. So we write it as, suppose we write the notation, we write tau ij, where I can independently take values 1, 2, and 3, and j can independently take values 1, 2, and 3. That will give you 9 values, which are here. We just use sigma 11 instead of tau 11 for convention. So if I wake you up in sleep tomorrow morning and ask you what is order, what are you going to say?
The number of directions to describe the components.
The number of independent directions required to describe a component, correct. And that is the first. The second important thing to remember is any 9 numbers or any, if you have, suppose you have a tensor that depends on 3 directions, I, J, K. And I, J, and K independently can take 1, 2, or 3, which means this will have 27 components. So any 9 numbers or any 27 numbers cannot just arbitrarily form a tensor. They still have to be obeying certain mathematical relationships such as invariants, so that their values scale correctly when the coordinates are changed from one system to another. In simple words, the choices made by an observer should not affect the observation. It's almost like saying if we have a experiment, whether you do it or you do it, if the outcome depends on who does it, it means that we are not doing the experiment or defining the experiment correctly. All right. Coming back to then some mathematics, can I erase this side? The usual philosophy I have for this course is I try to move the things forward slowly, because this is a lot of subtle things that come along the way. If you grasp the first 3 chapters correctly in the course, I really don't need to teach the last 2 chapters, because it's about just applying these principles to different examples. So we'll go a little bit slow in the beginning. Okay? I understand that, I'm aware of it. So we will extensively use matrix notation. So if we want to write, suppose if we want to write a scalar, we just write M. That is, it's basically a 1 by 1 matrix. It has only one number. A vector, as you know, will have 3 numbers, V equals Vi, Ei, which we can write as V1, V2, V3, column vector, or V1, V2, V3 as a row vector. And if we have a tensor, unless I explicitly say it, usually we mean a second order tensor. So if we write, for example, A with 2 bars, that is shorthand for A, Ij, Ei, Ej. I told you in this example that every component is defined by 2 directions. So if we take 2 directions and just put them next to each other, this is not a dot product. This is like putting 2 vectors together, but not really doing any operation with them. It's just like two vectors. This notation is called, or this entity is called, just like EI is a unit vector, EI, EJ is a unit dyad. You can write EI, EJ, EK is a triad, and so on. So we write A, the tensor, is represented by a scalar Aij, which is defined by two directions I and J. So we add EI and EJ. Okay. So when we just refer to Aij, the scalar, it is kind of implied that it forms part of a matrix of 9 numbers which together form the tensor. So in terms of thinking, this is the tensor. The tensor is a set of 9 numbers, and this is a scalar which is part of a set of that which is part of a tensor. Okay. So the word tensor itself refers to the collection of 9 numbers, not to any one number individually. And when I say component of a tensor, I'm talking about a single number, single scalar. So if you want to write, '74, wow. No wonder it's hot. So this A, we write it in matrix notation as A11, 12, 13. The reason we write matrix notation is it makes operations easier. So for example, think of Aij multiplied by Vj. And recall that summation convention, what did I say? If two indices repeat on different quantities, summation is implied. This is shorthand for summation j equals 1 to 3 Aij Vj. Or this is like writing Ai 1 V1 plus Ai 2 V2 plus Ai 3 V3. Now here is a quantity which has one index I. What would this quantity then become? Its order is 1. And what is a quantity which has order 1? Vector. Scalar is order 0. Right? So if I write Bi is equal to Aij Vj, the moment you look at this part, the first thing you would say is, I am going to sum over j. So after the summation, the j will be gone. And I'm left with I on each term, which will make this a quantity of order 1. That makes Bi the component of a vector. So what we are getting here is the product, or I should say scalar product of a tensor, and it's a second order tensor, even if I don't say second order tensor, and a vector is a vector. And how you would express this operation in terms of matrices, you have A11, 1, 2. I estimate that about 20% of my time in this class will be spent writing these matrices and 1, 1, 1, 2 and stuff. See. Multiplied by V1, V2, V3. So the same quantity, you are going to get a vector which is A11, V1, A12, V2, 13, V33, same 21, V1 plus 22, V2 plus 23, V3, 31, V1, 32, V2, 33, V3. This is a vector. Remember, this is just a number. At the end of it, it's just a scalar. So these three numbers lead to a quantity of order 1, meaning they are the components of a vector which we can give a name and we'll say B1, B2, B3. So this is the 3 by 3 matrix, 3 by 1, which gets you a 3 by 1. So if this is A, the tensor A, what is A transpose? What is the transpose of this matrix? So this A transpose, what is transpose? The operation, you recall? Row become column, columns become row. In other words, wherever I appears, replace it with J. Wherever J appears, replace with I. But the directions don't change. It's just for the components. So this is like writing A, Ji, Ei, Ej. And how will we write this in matrix form? A11 and A2. So just 1 second. So this is row 1 and this is column 2. So when I say 1, 2, this position is 1, 2, 1, 2 position. At 1, 2 position, I'm going to have A21. So this is going to be A21, A31, A12, A22, A32, no, 2, yeah, 32, A13, A23, A33. A transpose. So if I then calculate A transpose times B, that is if I write this matrix A11, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, multiplied by the vector V, which is still V1, V2, V3. I'm going to get, of course, you can write what the product is, A11, V1 plus A21, V2 plus A31, V3, and you can fill up the remaining 2. This is again a vector, but this is not the same as the previous one. As you can see, the difference. So this is A transpose times V, this is A times V. Okay, it leads to a slightly different vector. So if I write AI xi, AI xi, this is like writing same as A1 x1 plus A2 x2 plus A3 x3. If you just look at AI, since it has index I, you would say it's the component of a vector. Same with if you look at xi separately. Okay, so this you can write. This is, of course, you can recognize this as what? This is the scalar product between two vectors. Basically A dot x. Okay, you can write this as A1, A2, A3 row vector multiplied by x1, x2, x3. So this is 1 by 3, 3 by 1, which gives you A1 x1 plus A2 x2 plus A3 x3, which is nothing but 1 by 1. That's clear. Okay. So one of the properties of this transpose operation that we saw, you have A, you have a matrix A. Let's say we have a matrix A multiplied by B. And if you want the transpose of that, this will be equal to the multiplication of the same quantities but in reverse with the transpose. ABC transpose is C transpose B transpose A transpose. And this can be generalized to even more product matrices. And there is no real constraint on what type of matrix this A and B have to be, as long as they are compatible. This can be 3 by 3, 3 by 3, 3 by 3, 3 by 1, and so on, but this relationship will hold. I'm going to stop here today and we'll pick this up. So